small.
Oh.
Yeah. Yeah.
I was talking about the cold packs.
Why?
It was one thing, but it's really carbamide. It's not what it was.
What?
The cold packs.
No.
You told us it was something.
It's ammonium nitrate.
No, it's carbamide. It says in there carbamide.
It says what?
Carbamide in water.
What? I just bought 100 more of them.
He's bought a mystery.
Carbamide? I don't even know what that is.
Maybe it's just a fancy name for ammonium nitrate.
Let's pretend that's true.
They're like, let's call something fancy so no one copies our idea.
No wonder these are 10 cents a piece and made in China. Like, I don't even know what carbamide is.
Let's look
Are you looking it up?
Carbamide peroxide.
Well, that's H2O. That's hydrogen. I still don't know.
That's just hydrogen peroxide?
Well, so it says carbamide peroxide, but that's the Lewis dot structure for hydrogen peroxide. Thank you. I had no idea. I bought more, so I have like enough of these for the next 5 years, so I'm just going to keep lying. But seriously, the ones that apparently you buy that aren't made in China, they are ammonium nitrate. I don't even really, thank you. I didn't know. Anyway, but the chemistry holds true. Okay, so guys, we're going to do something different today. And let me explain to you why. And this has always been something I've sort of wrestled with at this moment. So guys, if you think about what we did last time in class, we literally talked for an hour about spontaneous, reversible, and irreversible. And guys, frankly, and I think I shared this with you, when we get into this conversation every year, I have no idea how it's going to go. And honestly, I get into these conversations, and when I'm looking at my notes before I'm with you guys, I'm like, there's no way this is going to take the whole class period. And yet it does every time. And it's awesome. And I have no idea how I pull that off. But it does. But guys, here's the thing. We've established the idea that spontaneity and reversibility is this way up there, really abstract, really, like, even at some level, hard to wrap our arms around concept. And yet, guys, we still have to muck around in the trenches. And we still have to do math. And we still have to talk about the nitty-gritty. So, guys, the question becomes, how do we live here but work here? You know what I'm saying? And so, frankly, this has been a weird tension that I haven't done a great job of resolving, but this is I have an idea. So what I did is I printed your class notes for you. Okay. So my hope in printing the class notes is not to trivialize the work we need to do. My hope is that as we tie theory into practice, we can take the focus off of, oh my gosh, I got to write down this equation word for word because you'll already have it. And then we can turn our attention to the theory that is then supported by the practice. Does that make sense? Then what I want to do is I really want there to be like 25 minutes left in class today, and I want to show you a Veritasium video. Yeah, so you know, what's his name? Derek Mueller. For a PhD physicist, he's pretty smart. But I don't know if you've ever seen him do the man on the street kind of things, where he goes out and once he walked on to Stanford and started asking people, how does the sun work? And all these like punky frat boys, and they don't know a thing, but they got into Stanford because of their parents. But guys, this is really, I don't want to say too much, but this, I seriously, and you guys know this, Big Brother is watching, right? I have not this year Googled or YouTube searched anything about entropy. Oh wait, I know how they did it, never mind. But all of a sudden my YouTube feed is full of entropy videos. And I was like, that, I know what happened now. I posted the screencast of the first part of Entropy, and it caught that. So anyway, so this just popped up in my feed, and I watched it, and I was like, my students need to see this. And so guys, we're gonna end with enough time to watch this video. Hey.
I'd just like to say that what you said earlier, I lie to you all the time, but you just don't realize because atoms are so small.
Yeah.
Possibly the funniest thing I've ever heard.
But you understand, I'm serious. But no, in all seriousness, it's why I don't like teaching physics. Do you guys know that I have a degree in chemistry but a minor in physics? Yeah, and I actually student taught in both. I student taught in chemistry and physics. And to your thought there, Nathaniel, I hated teaching physics because everybody has a background in physics, right? I mean, everybody's throwing a ball in the air and everybody thinks they know what's going on, right? And so in physics, you spend more time helping students forget about the stuff they think they know and less time actually teaching them what's really going on. They've actually structured a learning theory based on it, and it's called conceptual change learning theory. And it's actually the way they suggest physics should be taught is you should get kids in crisis where all of their perceived understandings fail, and then you can build them back up, right? In chemistry, you guys don't have any clue. Right? And consequently, I'm not undoing damage. We're just doing good work. Hey, buddy. I printed class notes for everybody.
Appreciate it.
You bet. Yeah.
So, it's about spontaneity.
Yeah, that's what I want to do. Let's do this. Guys, let's go to slide. That's not what I wanted. Slide. One of the slides. All right. So guys, what I'd like to do is I'd like to take us to this slide. And what I'd like to do is I'd like to draw our attention, and Dallin, this is not me ignoring your question, but guys, what I'd like to do is I'd like to have us rally around the bottom 4 points on this slide. Because guys, if we can say amen to these 4 things, then we can talk. So guys, here's what we know as it applies to spontaneity. The first thing we know is this: spontaneous processes have a direction. Balls always roll downhill, they never roll uphill. Methane and oxygen always makes carbon dioxide in water. Carbon dioxide in water never make methane, thank goodness. Imagine if our atmosphere spontaneously just turned into methane and oxygen. That'd be kind of bad. Then guys, number 3, if a process is spontaneous, happens on its own, the reverse process is never spontaneous. But guys, with all of this comes a caveat. Don't confuse irreversible with can't go backwards. Guys, we can force any process. We can move balls uphill. We can turn carbon dioxide into water and water into methane and oxygen. We can do that. It just never happens on its own. That's how spontaneity works. And then guys, finally, enthalpy is not enough to predict it. And we learned that interesting idea as we talked about our carbamide. Is that carbamide in water solution process? Because guys, when we popped this, energy went in, but it happened all on its own. So guys, we established a principle over the last couple days that says processes that release heat, enthalpy, tend to happen on their own. But now guys, we're finding out processes can happen on their own, but they take in energy. So enthalpy is not enough. That's where we are right now. What do you need to talk about? Finally.
So, is there, like, by looking at a formula?
Like a chemical reaction?
Yeah.
A reaction and not a formula?
Yeah.
Okay, yeah, go.
By looking at a reaction, is there
Absolutely. So guys, the question is this: is there a way to look at a chemical formula and figure a chemical reaction and figure out if it's spontaneous? And the answer is yes. And the question is how? And the answer is Hess's law. Okay, so if we can figure out the energy change for the reaction, and if that energy change is negative, exothermic, it tends to be spontaneous. Guys, that's part of the answer. Don't miss, guys, this is good stuff. So does that make sense? We can look at a chemical reaction, and if we can figure out its delta H, Hess's law, if it's negative, that tends to be spontaneous. Is that okay? But now we got a problem. Now, just give me ammonium nitrate, please. So this is ammonium nitrate. And guys, if we add ammonium nitrate, NH4NO3, breaking apart into NH4 plus and NO3. So guys, if we did that, we would find that the delta H for that process is positive. But it's still spontaneous. So what you're going to find out, Dallin, is that while the answer to your question is yes, there's more we need to do. So delta H gets us halfway there. If it's negative, it tends to be spontaneous. But there's another factor that we need to bring into the conversation to fully understand the answer to that question. And it's entropy. Guys, can we let that be our segue? Okay, so guys, way up here, this is like God, religion, and politics. These are big ideas. You ready? When reactions give off energy, enthalpy, they tend to be spontaneous. And guys, we can picture that, right? We experience enthalpy. We can feel the warmth of a fire. Guys, we have a tactile, very real experience of heat radiating away, right? But guys, what you need to understand right now, and this gets really abstract, guys, in the same way that releasing heat drives processes in our universe, so does changing entropy. But guys, we're going to define it in a minute, but at the end of the day, guys, here's the problem. You can't feel entropy. In many instances, you're not even aware of entropy. And it gets even worse because sometimes what you think you're seeing entropy do is actually not what it's doing. But guys, right now we need to start to invite into our thinking this new idea. So here's what we know. Enthalpy drives changes in enthalpy drive reactions. Reactions that give off heat tend to happen on their own, but some of them don't. So what's going on? And guys, the answer is the thing that drives these reactions is a change in entropy. Let's say that again. Guys, when enthalpy is not enough to describe what's going on in a process, it's the change in entropy that drives the reaction. Now guys, stop. Do you remember what we said the big idea was for this unit? Do you remember? Is a reaction spontaneous? And Dallin, without knowing it, I think, was asking that question. So the question is, how do we know if a reaction is spontaneous? Part of it's enthalpy, but the other part is entropy. And we're going to get into that today. And then guys, on the next day, what we're going to do is take enthalpy and entropy and mush them together. And when you take entropy and enthalpy and mush them together, guess what you get? Gibbs free energy. And that's where we're going in the end. All right? Here we go. Entropy. So guys, if enthalpy is not enough, we need ourselves some entropy. Guys, don't look at your notes, look at my paper. So guys, if you look at the notes, and you probably know the answer anyway, but guys, here's the deal. Imagine if you can 2 propane cylinders, like on your grill. And imagine that you could hook them together with a hose. And guys, imagine that the propane cylinder on your right is full of propane. And imagine that the propane cylinder on the left is completely empty. And then you open up the valve between them. What's going to happen? It's going to equalize. Now guys, do you have to squeeze the full tank to get them to equalize? Do you have to do work? No. Do you have to heat it up? No. Do you have to chant or pray over this to get them to equalize? Guys, do you have to do anything to get these things to equalize? No. Is it spontaneous?
Yes.
So why does it happen? Entropy. Guys, it happens because of entropy. So guys, let's use this as a simple understanding of what entropy is all about. And now guys, I've got to pause for a minute and think about what this is going to look like. Let's do this. Draw this with me. It's not in your notes. So guys, do you remember when we were reading over the chapter and there was that one lone bolded word on one of the pages and it was microstates? So microstates is not a part of the AP curriculum. But guys, as you get deeper into entropy, you're going to need to think about this. And the Derek Mueller video does an amazing job of talking about this. Way better than I'm about to do. But I want you to understand the idea. So guys, let's do this. I'm going to go red. Okay, so guys, imagine this. We are going to say that in the canister on the left, draw this with me. In the canister on the left, there are two atoms of, let's call them atoms, say it's, I don't know, neon. There's two atoms of gas. Now guys, when the valve is closed, where do those atoms have to be? On the right. They ain't got a choice. But now guys, when we open up the valves, what are the possible arrangements that we can end up with? Well guys, one of the things we can end up with is one here, but we're going to call this number 1. And then we could end up with one over here, and we're going to call this number 2. So guys, and we just need to keep track. I would switch colors, but it's too hard. So guys, what are other possible arrangements? They could both stay. So this could be a possible arrangement, and I'm not going to number them because they're 1 and 2. Guys, what would another one of the possible arrangements be? Go ahead, Regan. They could both be on the left. And then what's the final possible arrangement? Go ahead, JD. Oh, P.S. JD, about your chapter summary, you put it in the lab basket. I found it. Okay, now what's the other arrangement? One over here switched. So guys, 1 could be here and 2 could be here. Let me keep going. Now guys, do this. Let's talk about percentages. If these are our 4 possible arrangements, what percentage of the time are they both going to be on the right? 25% of the time. What percentage of the time will they both be on the left? Assuming this is random, 25%. Now guys, what percentage of the time will 2 be on the left and 1 be on the right? 25. Now, what percentage of the time will 1 be on the left and 2 be on the right? 25. But, guys, this arrangement right here and this arrangement right here, do you see that they look the same? We've got 1 atom in each container, and it really doesn't matter. Oh, I hit you in the head. We've got 1 in each container.
Teacher, please introduce the last names that begin with G through...
Guys, if you need to get retakes done, we'll do them 3rd period. But guys, do you get the idea that we could have 1 and 2 or 2 and 1, but it looks the same? So in total, what percentage of the time are they evenly spread out? 50% of the time. Guys, that is why they spread out evenly. These are microstates. We have 4 microstates. We got all and none, none and all, or 1 and 1. And guys, because 1 and 1 is the more likely option, that's what we see happen. But now you're going, wait a minute. What about the 25 and the 25? Now guys, do this. Take 4 and turn it into Avogadro's number. If we have Avogadro's number of atoms in one of these vessels, guys, what are the chances that all 602 septillion are going to be over here? 0. What about all of them being on the left? 0. But guys, what you find is as the sample you get gets bigger and bigger and bigger, you end up with a higher and higher probability of them being perfectly distributed through both. Does that make sense? Guys, that is the driving force behind this. So when you think about why do processes happen, they release heat, but they also do stuff like this. And so guys, this is what we call entropy. And at the end of the day, guys, this is just the universe tending towards the most probable outcome in any particular situation. But now, guys, this is where we get to our functional understanding of entropy. And it goes like this. Guys, if you've got 2 dots over here, that is relatively organized, if you will. Guys, if you've got a dot over here and if you've got a dot over here, that is less organized. We call it less random, higher disorder. So guys, at the end of the day, it goes like this. Entropy is the disorder of the system. Guys, this is the nugget. Entropy is the disorder of the system. Guys, never, ever, never think about order. If you think about order, you're going to get all your signs wrong. So guys, entropy is the disorder of a system, and all processes go towards higher states of disorder. Why do they do that? Because, guys, the law of averages says that the most disordered arrangement is also the most likely arrangement. Dang, y'all. You just learned the second law of thermodynamics in about 5 minutes using 2 stupid circles on the board. But, guys, that is it. That is the second law of thermo. So, guys, let's review and you can write down what you need. All processes, let me say it differently. Entropy is disorder, not order, it's disorder. Guys, entropy is disorder, and all processes go to conditions of higher disorder. All processes go to conditions of higher disorder. Why do they do that? Because the law of averages says that disorder is more likely to be the case. Just a second, Sharp, let people finish jotting ideas. But guys, you do of course understand the significant implication of all of these things, right? When your parents tell you to clean your room, you just need to let them know that you're just letting nature do its thing. Because guys, when your room becomes a mess, it's just the entropy is going up. Now, that's natural. Why fight it, right? Yeah, go ahead.
So, it's not all processes.
All of them. All of them. All of them. And that's the thing that makes this nasty. And I'm not going to give you the answer to the Mueller video, but that's the thing that makes this nasty.
I feel like some things that we do become, like if we were to force all of the gas
Yeah.
to the other cylinder,
Yeah. Yes.
then that would be more orderly.
Absolutely.
So that's a process that would reduce the entropy.
Yes. Guys, can we chase down Sharp's idea?
So is it just spontaneous things?
No. It's all things. So guys, let's just use this as the opportunity to jump into this a little more deeply. So guys, it is not just spontaneous things that increase entropy. All things increase entropy. So let's talk about your example. Guys, don't miss this. So imagine that we do that. Imagine that we take that and we shove them back onto this side, right? And so now that is more ordered. It's not spontaneous, but it is more ordered. We made that more ordered. But guess what? We became less ordered in the process of doing that. How did that happen? We broke bonds inside of molecules in order to get the fuel to give the push. And as we do that, we radiate heat out into the atmosphere. And I don't want to go, it tracks all the way back to the sun. We'll talk more later. But the idea here is that whether it's spontaneous or not, anything that happens causes the entropy of the universe to go up. And it may not be the system. It could be the surroundings whose entropy is going up. But guys, everything that happens, spontaneous or not, the entropy goes up. Just like an atom. The trick is you may have to look really hard to figure out where that entropy change is taking place. And ultimately, all of these entropy changes map back to the sun.
So you can make the entropy of a system. You can make the entropy of a system go down.
Absolutely.
But overall, in the entire universe, it's always
Yes, and so let's run with Adam just a second. Let's run with that. So the idea is we can make the entropy, as you said, the entropy of a system go down. But when we do that, the entropy of the surroundings had to go up by more. Okay, did that make sense, y'all? If a process's entropy goes down, the entropy of the surroundings had to go up by more. So guys, there is not a law of conservation of entropy. You know how we said that energy goes in and energy comes out and those are the same, system and surroundings, enthalpy? That is not true for entropy. Guys, there is not a law of conservation of entropy. If we look at the entropy of the system and the entropy of the surroundings, if the entropy of the system goes down, the entropy of the surroundings goes up by more. And so at the end of the day, everything that happens causes an increase in entropy. And guys, at the end of the day, the entropy of the universe is always going up. Yeah, you want to know the sad end game to all of this? In the end, the universe is going to become really, really big and really, really cold and really, really dark. Because as all of this stuff dissipates and becomes more disordered, life stops happening, stars stop happening, all of this stops happening, and we just end up floating around in a big ball of dark and cold.
That's not enough to give you the next.
So now, guys, we all hold hands and sing Kumbaya. Adam, go ahead.
So in my chapter 19 summary, I have this little equation about how for a reversible process, a net change in it in the universe is going to equal 0.
Good, let's talk. Okay, so guys, this is where, so we were just floating around in the conceptual clouds, right? Guys, let's land this plane and let's talk about this down in the trenches. So guys, we are going to then skip down to the next slide right here. Oops, number 6. Here we go. So guys, oh shoot, what I meant to say was here's your homework. Why isn't this working? Okay, here we go. So guys, let's talk about entropy. This is all in your notes. So what is entropy? Entropy is the disorder of a system. Do not think order. Never. Disorder. And so guys, it's abbreviated S. That makes sense, right? Yeah, just like heat is Q.
Well, it makes more sense than P is Q.
Why?
Because this.
Okay. But guys, fundamentally it's this, and this is not in your notes, but you may want to write it down if this is a concept that you possess. So guys, the more disordered or random a system, the larger the entropy. Why is that true? More microstates. I don't know if that's helpful to you, but guys, at the end of the day, the more things that you have and the more places that those things can be, the more microstates exist. So guys, to dig in this more deeply, we are going to consider dissolving salt in water. So what's our count? How many times have we watched this video so far? 4? Here comes 5.
When an ionic substance, such as sodium chloride, is placed in water, water molecules
Okay. So guys, what I want you to do is I want you to watch this video through new eyes. Guys, we have watched this video talking about ionic and covalent bonding. We have watched this video through the lens of polarity and intermolecular forces. We have watched this video through, what else have we talked about here? How solutions work. Guys, what I want you to do now is I want you to watch this video through the lens of entropy. Disorder. We're going to watch it twice.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Got it? I think I can just click. Okay. So guys, here's the question that I have for you. In the entirety of this video, is entropy going up or down? Talk with the person next to you.
If it's just a solid crystal, or it could be different ways you can extract it. And then water, because it could be any one of those, like any one of those water molecules, any one of those sodium ions together.
All right, all ready? Does entropy go up or does entropy go down? Up?
Up.
Down? You're all right. It's both. So now guys, watch. And this is the thing that makes entropy different than enthalpy. Guys, when we look at a process through the lens of enthalpy, heat, what we do is we focus on the system and we watch energy go in and out. Guys, when we talk about entropy, we have to broaden our view because there is no conservation of entropy. We will have entropies going up and down. So guys, let's talk about this. This is a salt crystal. Would you say this has high or low entropy, relatively speaking? Guys, solids, hear this, solids have the lowest entropies of all three of the phases. Can you picture that? Right? So we've got, I mean, you can see it really, I think, plainly here. So this is ice. This is liquid water. Which one is more disorganized? The liquid. Guys, this is going to come back to bite you on the AP test. That is one of the fundamental things they want you to know, is that the entropy of gases is greater than liquids, liquids is greater than solids. So, solids tend to be low entropy systems. You ready for an interesting thought? Can we make the entropy of this system lower, the salt? Can we make the entropy of the salt lower? How? Cool it down. So guys, at what temperature can we not make it any cooler?
0 degrees Kelvin.
Yeah, so I know that we've said that 0 degrees Kelvin, absolute zero, is the lowest possible temperature. Why? Because entropy becomes zero. Yeah, right? Guys, let that settle for just a minute. So the actual definition of absolute zero is the temperature, and I'm going to do this wrong, but guys, it is the temperature at which all the disorder goes away. It is perfect order. And remember, we don't talk about order. But guys, at absolute zero, there is no randomness, and it's absolutely ordered. Guys, that's why we can't get to absolute zero, because nothing will ever be perfectly ordered, because it's always got a little bit of energy in there that causes it to wiggle a little bit. Okay, so this is relatively low entropy. Now, guys, now, let's bring in the water.
When an ionic substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attraction.
Stop. Now, what is happening to entropy as this process continues? Is it going up or it's going down? Both. Yeah. So guys, turn your attention to the salt. Is its entropy going up or down? It is going up because the ions are spreading out into solution. Now they have more possible places that they can be, more microstates, they're more disordered, and entropy is going up, yes? Now guys, turn your attention to the water. What's happening there? It's becoming organized. Guys, these water molecules used to be chilling, hanging out, doing their water molecule mosh pit thing. And then you stick salt in there, and all of a sudden these ions are going, man, you ain't free to do that, because now we're going to get all locked together, and you have fewer places that you can be. So guys, the entropy of the salt is going up, but the entropy of the water is going down. Does that make sense? Okay. Now guys, don't take this too far. So does salt dissolve in water spontaneously? Of course. So we are not now saying that the entropy of the salt goes up more than the entropy of the water goes down, because there are other entropies that we need to keep in mind, because heat's being exchanged, this is exothermic, by the way, salt and what? No. Table salt and water is slightly endothermic. You'll find out that next week. So guys, this is not the whole picture about entropy and spontaneity. All that we're taking away from this is the idea that if we broaden our horizons, we will see increases and decreases in entropy happening at the same time. Yo? Okay. By the way, guys, when you get to this in your freshman chemistry class, this video will be posted. You're going to want to go back and watch it. Wait until you see what a college professor does with this. Yeah. Do you have your arm inside your... Yes, Nora.
So you said that the entropy is always going up,
It is.
except for the times when it goes down?
The total entropy of the universe always goes up.
Yeah.
So
Sometimes
like,
it's-
but if you have like a process or something, you're gonna have stuff going up and stuff going down. And
Correct.
you say that the overall, so like it
Yes.
cancels each other out to a point where it's going up.
Correct. Yes, that's fine. Yes. So anything that happens, we know that the entropy of the universe is going up. The thing that makes this tricky is sometimes it's hard to know where that's happening. right? So this is not the complete picture, which is why I was sort of waffling a little bit and going, hey, this isn't the whole picture. Salt's entropy is going up, water's going down, but that's not the whole picture. Why not? And the answer is because let's draw a beaker. And we now need to talk about energy, heat, delta H, that is moving between these things. So check this out. When something heats up, its entropy goes up. Right? Why? Because it wiggles more. And so the idea is that there is a connection between heat and entropy. And so in order to see where all of the entropy changes are, we've got to broaden our vision until we see all of the places where disorder is going up and down. But your thought is yes. In the end, if we could account for all the pieces, entropy is always going up all the time. How we doing? Good? Okay. So guys, let's then really get down in the trenches for a couple minutes. And then let's wrap this up. So guys, it goes like this. Second law of thermodynamics. And guys, the second law of thermodynamics, for our purpose, and again guys, don't Google it, it's simply this. When we talk about entropy changes, this is exactly where Nora took us. Guys, we have got to consider not just the system. We've got to consider everything. And when we do, the total change in entropy for a process is termed the entropy change for the universe, and this takes into consideration everything. And so guys, the change in entropy for the universe is then the change in entropy for the system and the surroundings. And understand, unlike enthalpy, where we just say system up, surroundings down, or vice versa, guys, now you'll notice the system and the surroundings are on the same side of the equation. One doesn't go up and one doesn't go proportionally down. But what does happen, whether it's spontaneous or not, if we could find the change in entropy for the system and the change in the entropy for the surroundings, we know that it's going up in every single thing that happens. The entropy of the universe is just going up. So guys, this is then how it leads to reversibility. But Dylan, let's pause before we get into it.
So, how would we find, numbers?
Good. This is going to come up in the slides in just a minute, but let's talk about it. Guys, please hear this. So, remember when we talked about enthalpy, energy, and we said that you can't directly measure enthalpy? You can't stick an energy meter into a block or into a chunk of salt and find out how much energy it has, so we do changes. Dallin, entropy is measurable. You can measure entropy. So how do you do it? And the answer is, what are the things that cause things to be disordered? Some of it is phase, solid, liquid, or gas. Some of it is the specific type of crystal, if it's a solid. Some of it is temperature. Some of it is mass. So guys, you can actually directly measure the things that tell us how disordered a system is. It doesn't have to be a change. Let that sink in for a second. Guys, it doesn't have to be a change. We can empirically measure disorder. But to do it, we measure the things that lead to disorder, which is complexity, solid, liquid, or gas, temperature, mass, those sorts of things. We don't have to do that in this class, but as you get deeper into chemistry, you will. So Dallin, was that okay? Okay, all right. So guys, now to your point, Adam. It goes like this. Guys, in a reversible equilibrium process, the change in entropy for the universe is 0. Okay? So guys, how do you visualize that? What does that look like? What is our example, if you will? What is our reference point for equilibrium? Ice and water. Ice and water at 0 degrees Celsius. So guys, think about it. So guys, here we have ice, right? Entropy, high or low? Low. Here we have water. Entropy, higher or lower? Higher. And then we've got a water molecule, and these should all be together. But guys, we've got a water molecule that sticks to the ice. What happened to its entropy? Went down. But that makes one of these molecules go into the liquid phase. What happened to its entropy? Went up. But those exactly cancel each other out. So guys, any process that is at equilibrium, its delta, its change in entropy is 0. But how does that tie into reversibility? Guys, is an equilibrium process reversible? Yeah, by definition. But guys, think about what reversible means. It means it's going in both directions at the same time, and the net change is 0. So as they're doing this, the net change in system and surroundings is 0, and that's why the delta S is 0. Good? Okay, now, what about spontaneous processes? And guys, the answer is in spontaneous processes, the change in entropy for the universe goes up. You okay? Okay. So now, guys, what we've got to do is this. Let's make it mathematical really quickly, and then we're going to call it a day. So, guys, the math of it looks like this. So guys, when we talk about enthalpy change, when we talk about enthalpy, and maybe Dallin, I fear that the way I worded this may have misled us. So let's say it this way. So guys, when we talk about enthalpy changes, we can talk about measuring change in temperature, which gives us change in heat. But guys, when we measure entropy, what we do is this. We can calculate the entropy of a substance by measuring, again, its temperature and its crystal structure and its mass and all these other things. So guys, in that sense, we can directly measure, and I know this is a little misworded, guys, we can directly measure entropy, not by measuring entropy, but measuring the things that lead to it. But guys, this is the thing that's weird. We call these standard molar entropies, and it's abbreviated S naught. But guys, the units are joules. This is interesting. Joules per mole Kelvin. Yeah, we got to do the so. So guys, what are joules a measure of? Energy. What are moles a unit of? Amount of stuff. What's Kelvin? So now here's what we know. Disorganized can be measured in joules. How screwed up is your bedroom? 1,000 joules. So Dad, it's going to take me 1,000 joules to put my bedroom back together, and that's a solid 3 Snickers bars. So feed me.
Personally, my bedroom is disorganized at 10 joules for every 1 kilogram.
Ah, so now you have to measure the number of things in your room in moles.
Less than 1.
Do I have an always on thing.
And then, guys, it also relates to temperature. Go ahead.
Oh my.
I just spent worked my butt off cleaning it this whole last 2 weeks.
So you realize that if you actually worked your butt off, you could figure out the amount of energy stored in your butt. What was that? Go ahead.
So, I'm making...
What are we doing? What? Okay.
So, this is... In a way, it's still just, energy over
Yeah, good for you. Yes. Yeah.
temperature.
Yeah, good.
And that's very similar to
Yes.
calculus,
Yes.
but it's kind of like the opposite.
Dallin, brilliant. Guys, let's make that connection together, can we? Because if you remember how we started this conversation, we talked about the idea that we're comfortable with heat, right? We feel it, we experience it, it makes sense to us at a physical level. But guys, it's harder for us to think about entropy. It's disorder. What does that mean? And we can picture a messy bedroom, and at some level we understand microstates. But when we look at the units for this, we start to see there's an overlap. In the same way that when we talk about things like calories, it's how much energy causes this amount to change this temperature, right? So I like the way you're thinking about it. It's kind of the opposite. But at the end of the day, we need to understand, guys, that it's still a form of energy. In the same way that enthalpy, heat, is a way to move energy around, so is disorder. It has the units of energy. And as a result, gaining and losing entropy is another way to move energy around. What you're going to find in the Mueller video is they're even more tightly related than just that. But guys, there is one thing that we need to touch on. When we do delta H's, what are our units? What do they tend to be? Kilojoules per mole? Yeah? Guys, when we do entropy, they tend to be joules per mole, Kelvin. And this is going to become important. Guys, entropy changes tend to be smaller than enthalpy changes. Enthalpy changes get measured in kilojoules. Entropy changes get measured in joules. And that's going to be important because think about what we're doing next time. We're bringing enthalpy and entropy together, and that's Gibbs free energy, and we got to be careful of units. But Dallin, that's exactly the point. That when you start to see this connection between enthalpy and entropy, and I love that the units got you there, that's Gibbs free energy. Because when we bring those together, we have a whole new way of thinking about energy, and that's Gibbs free energy. You guys okay? Let's do this and wrap this up. So guys, where are we then headed with this? I don't think you need to grab your AP equation sheets. You've already seen it. So guys, here's what you need to know. Elements have entropies. Adam and I still haven't talked about this yet, but do you remember how we said the heats of formation of the elements are 0, right? Guys, the heats of formation of the elements are 0. So when we're doing enthalpy calculations, the delta H for elements is 0. We're saying that no energy is involved in the formation of elements. Again, we'll talk. But guys, that is not true of entropy. Guys, elements have the ability to be screwed up just like anything else, disordered. Then guys, as we said, these are phase dependent. We'll talk more later. But guys, the entropies of gases are greater than liquids or greater than solids. And guys, this also tends to change with mass. The bigger something is, the more massive it is, the more screwed up it can be. But then guys, also this. It also changes with complexity. The more complex a molecule is, the more screwed up it will be. But guys, interestingly, it also changes with elongation. If you have a molecule, guys, if you have a molecule, and I'm just throwing something stupid together, octets. That comes back to my original thought about my job being easier if I didn't have students. Go for it. So guys, if you have a molecule that's all long and stretchy and like this, can you see that it can get all wiggly? And that's more freedom, more microstates, more entropy. But if you ball this thing all up, it's harder for it to be wiggly. So guys, longer molecules have higher entropy than balled up molecules. There's an example of this in your book. I don't know that you need, oh look, guys, on page 808 it talks, oh, there's our microstates thing. I should be a teacher. I know. Oh, maybe they took the picture out of our book. Never mind. There should be a picture in the book. You can have that, but it's gone. Ooh, that's an amino acid. It is, but it doesn't ball up. So then, guys, this. Check it out. Guys, in the same way that we can calculate entropy change or enthalpy changes, the heat of formation of the products minus the heat of formation of the reactants, there is a similar equation for entropy change. It's still products minus reactants. It's still relative to numbers of moles. That's not in the AP sheet. But guys, what is the one glaring difference between this equation and the delta H equation? Go ahead. No, I don't think it has either on the M or the N, but it's just number of moles. Do you see it? Guys, there's no deltas. So here's the deal. If this was delta H, then this would be the heat of formation of the products, delta H formation, and this would be the heat of formation of the reactants. Guys, remember those values are how much energy is gained or lost when a mole of that compound is formed from its elements. But guys, when we talk about entropy, these are not entropies of formation. This is how messed up is that thing just sitting there. It's not how much did its messed up change when it got made. It's just how messed up is it? What's its entropy just sitting right there? Is that okay? Okay, guys, we're done. Let's watch this video. You've got your homework in your notes. So guys, there's a very real chance that showing this to you is a violation of copyright. So I'm going to stop recording.